Question 9 then begins just with asking us what would be observed if this dissolving process happens. So the first thing obviously to say is that the solid disappears. So it's obvious, but it doesn't mean you don't have to say it. Remember, it's always important to state the obvious things as well as the more subtle things. But the other thing is that it tells us that delta H is positive. And remember, positive means endothermic, and endothermic means heat gets taken away, taken into the bonding in effect. So if heat is taken away, it gets colder. So we can say the temperature decreases. Okay, so those would be the observations. And then it wants us to calculate delta S. So for that, always start by writing out your definition of delta G. And then you have to rearrange it. So if we move the minus T delta S over there, we get delta G plus T delta S is equal to delta H. And then we can bring the delta G over here and get T delta S is equal to delta H minus delta G. And then we can slide the temperature diagonally over to here and get delta S is equal to delta H minus delta G over T. Okay, so as always, it's very important to do that algebraically. I mean, you don't have to show the intermediate steps if you're comfortable rearranging things, but that's the safe way to do it a bit at a time. And that's your expression that you're then going to use. So now we've just got to put the numbers in, but remember, as always with free energy calculations, it's about being very careful with the units and also with the signs. So we're talking about 25 degrees C is the temperature for this. So let's put the numbers into there. So we get delta S is equal to delta H, which is plus 28.1, minus delta G. So this is where you've got to be careful, because it's minus 4.4 over T. T is 25 degrees C, but that has to be in Kelvin, so we add 273, which gives us 298. Okay, and then if you like, just to be on the safe side, you can rewrite that to make it explicit that subtracting a negative number is the same as adding a positive number. So it's plus 28.1 plus 4.4 over 298, which is plus 32.5 over 298, which, if you crunch the numbers, is plus 0.109. And that will be in kilojoules per Kelvin per mole. Okay, and that's where you've got to be careful, because that's not the usual unit for entropy. We normally use joules per Kelvin per mole, but it comes out in kilojoules because the numbers you fed in had kilojoules in the units. So that's in kilojoules per Kelvin per mole, and it doesn't specify what units it wanted, so you can leave it like that if you wanted, but if you wanted to change it, or you were told to change it into joules per Kelvin per mole, we can say that that equals, and we multiply by 1,000 to go kilojoules to joules, so it's plus 109 joules per Kelvin per mole is the answer. Make sure on all these numbers, delta H, delta G, delta S, that you always have an explicit sign. So it's not just 109, it's plus 109. That's important. Question 10, we're given the delta G and we're given the delta S, so we can calculate the delta H. So again, the first thing to do is write down the definition. Delta G is delta H minus T delta S, and then rearrange it. So always write it down first, then rearrange it. So you can see all we have to do this time is add T delta S to each side. So we get delta G plus T delta S is equal to delta H. So it's an easy rearrangement this time. And we can just put the numbers in with the usual precautions. So delta G is minus 24.0 plus T, 200 degrees C, but we've got to add 273 onto that to get Kelvin, so plus 473 times delta S, and delta S is plus 125 joules per Kelvin per mole, but that's got to be in kilojoules, so the units are compatible, so we divide by 1000, so times 0.125 kilojoules per Kelvin per mole. So you've got your numbers there, and you can then just plug them into your calculator and you get plus 35.1 kilojoules per mole for delta H is the answer. Question 11 is asking about complete combustion of methanol. So it doesn't give you the equation, but that's what it is. Remember that when we're going to use delta H of combustion, which is the number you're given, it has to relate to 1 mole burning to produce the product, and that means that you have to live with the half in the equation. You can't double it to get rid of the half, as you might sometimes be tempted to do. So that's the equation that we're talking about, and it gives us the delta H and it gives us the delta G at 25 degrees C. So the first thing it wants is the delta S. So remember that you always start by writing down delta G is delta H minus T delta S. That's the definition that forms the basis for answering all these questions. And then we've got to rearrange it to solve for delta S. So if we add T delta S to each side, we get delta H plus T delta S is equal to delta H. Okay, so let's just move that term over to there. Then we can move the delta G term over to this side. This is all because we're trying to get the delta S term on its own. So we've got T delta S is equal to delta H minus delta G. And then we can divide both sides by T. In other words, slide the T diagonally over to there, which gives us that delta S is equal to delta H minus delta G over T. Okay, so that's the relationship that we're going to use. So now we can plug these numbers in. So we've got that delta S is equal to delta H is minus 715 minus delta G. So we've got to be careful here with the signs because delta G is a negative number, so it's minus 691 divided by T. T is 25 degrees C, so we have to add 273, which gives us 298. And again, if you're not confident about that, it's worth explicitly rewriting it as saying that's minus 715 plus 691 over 298. And if you crunch the numbers, that comes to minus 0.0805, and that will be in kilojoules per Kelvin per mole, because the numbers we fed in, delta H and delta G, had kilojoules in them, so this will be in kilojoules as well. So that answer is fine, but if we wanted to go to the normal entropy units, we would have to multiply that by 1000 to change those kilojoules into joules. So we can say that that equals minus 80.5 joules per Kelvin per mole. Part B is asking us to use this delta S that we've just calculated in part A, together with the molar entropies that it has given us in the question, to calculate the missing one, which is the molar entropy of methanol. So remember, the way it works is that delta S is equal to the molar entropy of the products, because you've gained the product in the reaction, so you have the entropy that they possess, but minus the molar entropy of the reactants, because you've destroyed the reactants, so you've lost the entropy that they have. So if you just think of it like that, you get that the right way round. So we can substitute numbers into that. So delta S is minus 80.5 is equal to, so S naught of the product, we've got 1 mole of CO2, so that's 214. And we've got 2 moles of H2O, so that's 2 times 70. Okay, so that's S naught of the products, 1 lot of CO2 and 2 lots of water, and then minus S naught of the reactants. So the reactants we've got our methanol, which is X, that's the one we don't know, so we'll call it X, plus 1.5 lots of oxygen, so 1.5 times 204. Okay, so then it's just a case of rearranging that to solve for X. And as always, the thing to do is do it in as many stages as you need to make sure you don't slip up. Don't feel you have to do lots in your head or whatever. You know, it's better in the end to take a few more seconds to work it out carefully. So we get that that is equal to 214 plus 140 minus X plus 306, which is equal to 354 minus X minus 306. And then you can just fairly straightforwardly move things around, and you should come up with X is equal to 128.5 joules per Kelvin per mole. Okay, so that's just a case of using this, which we had in some of the earlier questions, but now bringing in delta S that we've calculated, and just using this idea of introducing X as the unknown, which you've used lots of times in enthalpy calculations and things. Okay, so that's that one.